Repeat some of the slides from yesterday. I just want to slow down a little bit. Hopefully you can ask some questions if you have. And then I probably, as some individual, other individual example, just stop a little bit and ask if there's any question you feel like we can discuss a little bit more specific application. So as I say, the application of the state space model for neuroscience analysis, essentially you want to, the goal is trying to develop some techniques, statistical techniques, to characterize the nature, the dynamic nature or stochastic nature of the data you observe. So then you hopefully can come up with some, either you get some nice interpretation of the data or you try to prove some hypothesis. So as you know, right now, nowadays the technology advancement really give us a lot of opportunity and freedom to collect simultaneously, sometimes collect simultaneously a lot of data, different modality, either intracellular recording or extracellular recording, sometimes both simultaneously. The extracellular recording, for example, they may include spike, field potential. In the human subject, typically the non-invasive recording, you have EEG. For the invasive recording, sometimes you have this sort of a ECOG signal, which is typically found in the epileptic patient before try to identify the seizure. And for the non-invasive recording, you have MAC or fMRI. We have here a lot of calcium imaging example yesterday. And in many cases, you also collect sometimes a behavior response. For example, the animal or human doing sort of recognize, present some sort of a stimuli the animals require or trained to do some tasks, then either make a correct response or error response. So the response could be a binary variable and sometimes could be a multinomial variable, like a categorical variable. So then you have all of those signals, and hopefully you can using those data to, according to your hypothesis, you want to answer some scientific question, you want to develop some model and fit those data. So here I basically list this 8 representative example that come from literature, and this mostly they are representative and in terms of using state-space model for analysis. The first example is decoding. The second example is neuroplasticity in terms of receptive field, how the receptive field change according to experience. Sometimes just in time, like simultaneously during the specific trial. Then you also dealing with the between trial. Sometimes you have this, you can call it plasticity or neurofiring, this variability. You observe that. Say, for example, animal doing learning, then you observe this variability across trial. How to characterize this between trial variability. And the fourth example is involve the behavior analysis in learning in terms of either dealing with the animal or human subject. That example involved like during the deep brain stimulation for subject required to perform certain tasks, and then how to model that the data. The fifth example is very standard in terms of just like you have a spike train, you observe a spike train that depends on your temporal resolution you care about, you want to estimate the firing rate function in the one-dimensional case. And sometimes it's a multi-dimensional. For example, you want to characterize the orientation tuning of the V1 unit or motor unit. So in that case, it could be multi-dimensional. Then you can use the state space model, or in general, either an EM algorithm or NCMC kind of inference to estimate. Then this number 6 example, I figure I should tell you a little bit about the sort of EEG or MEG example. Even I didn't really spend a lot of time to talk about that. Just give you one example how to they come up with this elegant solution. So, and then next I also present one example of how to do deconvolution of an fMRI time series. I think the beginning of the tutorial I give you some 1 or 2 slides how to do deconvolution of the calcium imaging deconvolved spike chain, but this is just the bulk of the underlying signal is a continuous signal. So last example I'm going to talk about in terms of a brain-machine interface example in terms of how to do optimal feedback control. Then you have like how to incorporate the control signal to your state space model, and then how to design the control signal. The first example, I think I already told you a little bit yesterday, involved the hippocampus decoding, how to using, in this example, so you have the rat navigating in the open field 2D environment. The typical procedure in the literature is that you first collect the data, and you have some training data, and you do some encoding analysis. By encoding analysis, you're already assuming the spike has been sorted. So this is standard approach. Of course, there are other approaches can sidestep this procedure. But typically, you do spike sorting, and then encoding analysis. Basically, you want to construct for the unit. You construct a receptive field. This is like a 3 receptive field shown here. And then, since you have the receptive field, and then you can come up with a light field model, right? And then the decoding stage, you're going to make assumption about the animal's movement, how the animal make a movement in that environment, making such an assumption. That model can be also fit using your empirical data during the training phase. And then with the spike data again, then you just plug in, based on the state space model, you can just use the base rule to do a straightforward analysis. So in the early work by Emery Brown and some people in the lab, what they do is to fit this in the encoding analysis, just fit this position model, essentially assuming animals walk for sort of a continuous model like a random walk or AR type model. The limitation of this is basically assuming everything is continuous, it's smooth, right? But imagine that sometimes the animal making a dramatic turn, and thus you have sort of discontinuity. So in that case, you will expect the model will not work very well. So occasionally you see it doesn't work very well because there's assuming continuity. So for the receptive field, for a small environment, typically people observe the receptive field can be modeled by a Gaussian or like a generalized Tyson model with a certain basis function, and the basis function is associated with a certain linear coefficient. You just fit the regression parameter. But this is you decide this basis function. It's a finite, in this case, a finite orthogonal basis. So you adding change. When you're adding more basis function, it doesn't really change the coefficient, but the rest of the coefficient, they are orthogonal to each other. So I have to point out the limitation of this. This is early work, and then recently people found that if you have a receptive field, which is a multimodal, so sometimes a single univariate Gaussian, even a single mode Gaussian model might not be sufficient. So we see in one of the slides I showed you in the other talk, basically in the linear check case, you have a receptive field, sometimes you have multimodal. So multimodal case, a single Gaussian cannot characterize the receptive field very well. So of course, you can use it in a single dimension, you can use it in the spline model, the spline, fitting the spline, and then, for the one-dimensional case. But for two-dimensional case, if you're using the spline model, maybe it involves some computational issue of how to fit a two-dimensional spline. So anyway, so this is the general idea I want to point out. This is early work of when you deal with the real data, you need to confirm whether this model is actually accurate and whether it's sufficient. So this recently using this Zernike polynomial, so the individual basis is orthogonal to each other. So essentially, you can just sum when you have sufficient number of the orthogonal bases. Then, in theory, in principle, you can construct anything represent anything you want. Yeah, and that's, I just show you some example here, and that's what in the paper recorded by the area in 2004 neurocomputation paper using this Zhe-Chen polynomial, and they also compared the Gaussian receptive field model. Yeah.
I don't know why the Zhe-Chen polynomial is important. So the Zhe-Chen polynomial is, this is the basis of the
global approximation.
Yeah. But actually, so the neural network, neural perspective is local.
Yeah.
But it can represent, but it seems to be no scientific reason for using the scientific polynomial, I think.
Well, here basically I'm not arguing whether the receptive field, I mean, obviously it's local. You see all the example, you see the receptive is local. The question is that how to represent anything very non-structured, right? Because all the thing has a very clear structure. Receptive field has structure. The basis function has structure, and it just generally is hard to find a principal way to find a basis function, and then you can construct certain I believe you can find other type of basis functions in the two-dimensional circular. The reason using Zhe-Chen polynomial is because here the basis is defined on the circular thing, circular area, so it's like completely circular. The basis, the support is circular, so it's convenient to define this basis function for this open field environment, just for that specific reason, I believe. And I don't argue, I'm not suggesting that this, even using a large number, is good enough. I'm not suggesting that. Actually, it's not. So when you have a very complicated receptive field, I mean, this still doesn't work well. I mean, just to some degree approximated. But at least it's a better approximation than Gaussian. But this is not I'm not saying it's the best.
Thank you.
Then after you do the encoding analysis, you're assuming all of this basis function, you can write it down already. So with this associated this the regression coefficient about the generalized linear model. So the decoding analysis just run like a point process filter in a similar way like Kalman filter. In the first two steps, just doing the prediction, it's just like linear equations, or just very similar to Kalman filter. In the update state, in the posterior state, basically it's a little different because here generally the update equation here involves some nonlinear. I mean the update of the likelihood of the point process likelihood, and the posterior variant basically involves this what is called Gaussian. In order to get this analytical form, so basically you want to approximate in the second step, you want to approximate by Gaussian, even if it's not Gaussian. So if it's a Gaussian, you want to characterize the mean and the variance. And then involves how to do the Laplace or Gaussian approximation. I described it yesterday. The exact derivation I won't go over it here, but just basically I tell you what's the principle of doing that. And obviously this is just one, the argument. I mean, they have some discussion in the paper, essentially why the Gaussian approximation makes some sense. One of the intuition of Gaussian approximation is that when you have a lot of number of units, C, so the Gaussian approximation is the law of large number. If you have a lot of units, so the Gaussian approximation is worse better. So the approximation worse better when C is large. So there's some analysis about how the approximation accuracy compared to the number of units. But if you say, imagine only have one single neuron, the Gaussian approximation might work very poorly. But the assumption is that have a lot of when you have a lot of large number, the Gaussian approximation makes more sense. So in the 2004 paper neural computation, they do compare the standard method, but we're using reverse correlation. and compare the different sort of recessive field model, Gaussian model, and the Zwicky polynomial model. And you see the Zwicky polynomial model in the second column, overall the performance improved in terms of decoding accuracy. For that, you can basically, in the paper, you can characterize not only by the decoding accuracy by mean square error, you can also compute the information rate, entropy rate, and those are the information theoretical metric related to the Point process filter. So I won't show the video here because I showed it yesterday. And then after a few years back, there's a graduate student come to the lab and they say, whether we can do a little better because we talked about sequential model Carroll method yesterday, whether we can combine a sequential model Carroll method with this technique, right? So I don't know if you remember. If you don't remember, I can go back to the sequential model Carroll method. It's essentially, the key idea is that you want to sample the data, whether you draw the particle from a certain proposal distribution. And the proposal distribution is very important because it gives a very informative way to represent posterior. So what they do in this paper, they basically have compared the two types of particle filter. One is the basic particle filter, so the basic, just using the standard transition plier as the posterior and use the important weights proportion to the likelihood. These two basically, just one of them is using the point process filter, so you have a Gaussian approximation here. So here, this is Gaussian, the Gaussian mode. So I can draw sample from this Gaussian. We have the mean and covariance. I can draw sample from the Gaussian, and then using this particle from the Gaussian, and hopefully get better representation based on Monte Carlo. So it turns out yes.
Sorry. You mean that you use in the second one, so you use the Gaussian approximation for proposal distribution.
Right. Yeah. So the proposal is a Gaussian, but it's a Gaussian. It's not the transition ply Gaussian. It's not the transition Gaussian. It's not that transition ply. This posterior.
Yeah.
Which is a Gaussian approximation. So which is hopefully you already come up some two-stage process. First come up this, and then draw sample from that, and hopefully this give you a better estimate. But the computational comes in because you have to do some matrix inverse, right? So if you try to avoid the matrix inverse, what they do is that they try to use some updated learning rate. So this is a different notation. I apologize because the different papers use a different notation. So what they do here is basically using a learning rate update rather than you see here. This involves this term, and this term have to do a matrix inverse at different stage. So they want to avoid a numerical issue and try to reduce the computational complexity. They're just using this gradient update rather than update the second order covariance matrix. So for that they compare different number of particles and see the result, and then this compare the mean square error. You see the result. The second one is just the full version based on the full covariance update. And this is approximation using the learning rate. So the performance is similar, but in some cases the result is slightly worse, but it's comparable. So also you see that by using a lot of the particle, the result, the difference becomes less and less. The difference becomes smaller. But when using small number of particles, a good proposal distribution will make a big difference.
So how many dimensions of the state space of the model?
Well, in this case, just two. X, just the two-dimensional position.
And so I'm asking some more general questions about this is the model of the press field
Yeah.
Yeah, so, but there's another perspective, grid cell in the hippocampus. So, is there the research about the grid cell,
Grid cell, yeah. Well, the grid cell is recorded from entorhinal cortex. They have some sort of grid structure. Obviously, the receptive field have this grid line structure. What's your question?
Yeah,
Question?
yeah. So, is there something through the combination of the grid cell and grid cell and this statistical model? Is it research?
No, I mean, to my knowledge, the grid cell, in terms of people come up with some hypothesis, like a sort of a computational model of how the grid cell are generated based on the winner-take-all sort of a competitive sort of a nature. It's a hypothesis, like a computational model, sort of hypothesis. It's a computational-based model. It's really different from how to fit the data. So we didn't really have the grid cell. I mean, we have, but just we didn't use it. Grid cell basically contains certain information, but it's not that directly related to how to represent space. It is an exact position. Basically, when you go into the environment, different location, the cell will fire, like as a grid structure. So it doesn't give you a unique sort of one-to-one representation. So that concludes the hippocampus decoding. But the principle to other areas is similar. Basically, in a motor game, you want to characterize the encoding as you want to characterize unit. You have a tuning curve. You want to characterize the. In this case, you have a cosine tuning curve. So you want to fit this tuning curve in the encoding analysis, and then use it in the states equation. Basically, in this case, you consist of this is two-dimensional, I believe, two-dimensional position and the velocity. So you can construct this thing with a state-space model based on the kinematic equation relationship. And then in their work, they basically also using the particle filter approach. They construct, estimate the receptive field, and then assuming the likelihood is the possible likelihood using the spike count, like a large temporal beam, I believe is like 80 or 100 millisecond, order 100 millisecond. And then you have a number of unit m, then just the product, given the hand, there's a velocity. And what they do, assuming the velocity, assumes some smoothness. So essentially the smoothness, the velocity, then you construct an augmented variable and assume the smoothness. You can write down the new state equation. And compared to that, you enhance the, sort of put some point about the smoothness about the equation. So they then do some simulation. They also have some real data analysis, but for that illustration purpose, I just want to show you the for clarity is for showing the simulation only. And you see a difference between this two standard approach, population vector approach, and the OLB is a sort of a regression, standard regression approach. And then compare the particle filter. I forgot in this slide how many particles they use. But you see the trajectory is much smoother because we have using the state equation really impose the prior with a smoothness, so it's much smoother because of 2D trajectory. In the other approach, basically you lose this structure.
What is the population vector and pure OLE? So this is different between the model.
Yeah, population vector essentially just showing sort of a firing rate directly request to your firing rate is the firing rate request your firing rate vector. You have a vector for NVD to your input variable. It's like a position, and you have just a linear relationship. It's like a linear regression. I believe OLE is a little extension about the population vector. I forgot the detail. But basically, it's a linear regression approach.
This part which is the point and process-based approach.
This particle filter, yes, it's not quite process. It's spike count. It's a Poisson. So because they only care about large beam size. But for the hippocampus case, they do using spike timing, so it's like 5 milliseconds, like 2 milliseconds. Very few temporal, 5 temporal resolution.
So this is the main reason the difference. So this is a linear relation, but so this particular filter is using the so fine rate.
It's still fine rate.
And so again, linear. But it is also particular filter case is also linear.
The temporal resolution is the same. Comparison is fair because of data. It's just assumption. This is assuming Gaussian because the linear regression is assuming Gaussian, and this is assuming the Poisson, right? And state space model also gives certain structure because the state equation gives some smoothness about the velocity.
This is critical.
Uh,
Yeah, the Gaussian and Poisson, the difference is critical.
yeah. And also it's not smooth. It's just, you see the smoothness is imposed in the solution. And essentially, this is another example of showing that a different trajectory, the solution, the seamless observation observed. The next example, basically, I want to say something about the receptive field. The receptive field sometimes it can change during the ongoing activity. You can see that the receptive field is changing around time, even within the trial or within the lab, multiple lab, and the animal running environment. So the idea here is that you have an empirical model, like a parametric model, then characterized by certain parameter. For this example, it's showing the Gaussian, but it can be any type of a model, which is characterized on unknown parameter theta. So then you just want to write down a likelihood, and this likelihood, because you want to do adaptive filter, so the likelihood will be instantaneous likelihood. You're only using the single point observation rather than accumulated observation. So you just write down the likelihood. When you take the gradient of the likelihood, take the derivative of the likelihood with respect to theta, and then update the sort of like the gradient ascent, increasing using small step sign, gradually increasing the likelihood. The idea is very simple, so it's nothing complicated. So then you can see the result, you can track this, around this is simulation. It's showing the around time at different time point, the receptive field change, and then you can the filters are able to track the shape of the receptive field. And the other day, yesterday I showed some video in terms of the simulation. There's a video track the receptive field shape. It's very simple.
How the time window is selected?
Here, I believe it's like on the millisecond level.
Time window for the time window for the tracing the changes of the phase field. So
Well, this the sample, of course, is limited by the sampling frequency of the sampling frequency typically is very high, right? You have the sampling frequency in terms of the behavior, not only behavior, but also the spike. You have a spike, right? Sampling frequency is very high. In principle, you can track on that temporal resolution. But sometimes you don't need to, so you can track in a resolution that you are interested in. But I think for that word they use in millisecond, because the observation of the point process is 0, 1. In that simulation, just using one receptor, one unit.
My question is, they estimate the phase field.
Yeah.
In certain field.
Right.
And then they change, they apply the same method to the second field. So
It just continues to track.
Just
continues. They never stop. Start from the beginning, you have some initial condition, you might be a little off, and then just continues to track. Yeah. Of course, initially it takes some transient stage to track the true solution, but then after that, hopefully, just like a least square LMS filter, you will hopefully converge the steady state. If this, But this is showing it's non-stationary, right? Data is non-stationary, so it's a receptive field change, and the data basically come from different distribution. So if you it's still the non-stationary. And the third example also, we see this non-stationary example as well. We see this, if some unit along the tri, even you do a PSDH, from this plot you won't see this, you will not see this relationship about this tri-variability in terms of non-stationarity across tri. And the question is that how to characterize this tri-variability. The idea is that this first start with this, a simple model like a generalized linear model to fit the array with some sort of a set of a parameter function, a certain basis. The basis function could be, like indicator value when you have certain bandwidth inside. This basically will cover the PSTH. And then you can impose some smoothness and then using spline function, and then you have a smoothness on top of it. Then the basic model is just showing tri by tri variability. You can show this is for the random walk of those parameter theta, and then basically random walk allows you a certain continuity. Yeah.
Sorry, I lost the timing. About the previous topic,
Yeah.
could you comment on the functional meaning of the plasticity of the place field, like short-term memory or something? I don't know.
Well, I won't be able to comment that much in terms of make a deep connection about the synaptic plasticity of hippocampus to, shorter memory, this sort of deep question. For that study, to my knowledge, basically, they just want to demonstrate what the motivation is that during the experience in certain session, hippocampus, you see the receptive field remapping. So, when you change the environment or according to the experience from the normal environment to familiar environment, you see this receptive field might remap in the hippocampus case. That's the physiological finding. So the question is that, yeah, but the remapping typically happens in a longer time scale, not millisecond time scale. But the question is that if you just want to track whether you can able to track this receptive field if it happens in a very short time. So for example, you change the environment, so the hippocampus run the environment, you change the size of the environment. So the receptive field typically become bigger, right? So you have environment, so you have environment like this big. So receptive field is this. Now during the course of the experiment, you change, you make it bigger, and the finding is that the receptive field typically becomes bigger.
Yeah.
This could happen very quickly in the second time scale, in the second level. So then the question is that are you able to during the course of the experiment track the change of the receptive field?
How much is the time scale of the plastic change of the place field?
For that study, for the paper, is really based on simulation. I think it's just natural behavior. It's the natural behavior. So the animal runs the track, and showing the animal runs like a 10 centimeter per second around typically 3 meter long.
So typically all those seconds or
Could be, yeah. Could be, yeah.
thank you.
Yeah. So, okay, where am I? So, yeah, so basically that study is showing using fitting the GLN, and you basically fit, this is basically, space model you have to solve an EML with them. And this is just using the standard sort of naive way doing PSDH type of analysis. This is using step function, this is using the spline function. However, you see the model fit is not perfect. The reason for that, yeah.
I don't know, what is the figure? Explanation of the figure of the horizontal line, vertical line, is our figure.
This figure?
Yeah, yes.
This figure just is a 3-dimensional plot, this figure.
So,
Trial,
trial, okay.
time, and intensity.
The peaking intensity is
Yeah, just basically fit the rate around time and the trial, and then you have the final rate, instantaneous one. Right? You can use the two-dimensional plot, but just color image, but this shows three-dimensional plot. And you see, the reason you see this is no smoothing, because using a beam, and this you're showing some, when you're using spline, it's the smooth, right? So then, further to improve the model, you can incorporate some sort of spike history. And then by using some model selection here, you can use a 9 parameter of the spike history, then you can fit the data better. So also you're assuming theta, this is depends on the trial, so theta is a variable depends on the trial, but gamma is independent of the trial. So basically gamma is characterized as an intrinsic neuron property. This is only depends on certain property like refractory period or dependency is independent of the trial. So that's the assumption we made. And the theta is dependent on the trial, depends on the experience.
What is the why? Why I?
Gamma,
Gamma.
yeah, it's a parameter you want to fit. So this is no, this is a spike count.
Yeah, but so n k minus phi by.
Why?
What is why?
Phi, I think is, I believe the notation is K. K is a trial. R index is the basis function for the spline. So I is the number of the, I index is the number of the history window, how many bases you use is 9. And K is basically the trial. So for individual trial, I think you're just using, I believe 5 maybe it's like using 5 millisecond window or something like that. 5 times I, and then just moving back, 5 milliseconds. But the index here is not important. I mean, just assuming you have certain dependency of the spike history. You can choose in any window size you want. Because that spike history you observe, right? So current time is any time t, you can look in at the spike history, say the previous 5 milliseconds, and then 10 milliseconds, or 50 milliseconds, and so on. I mean, the notation here is not that important.
Mostly for the non-Poisson features introduced here.
Basically, just if you have spike history dependent, it's non-Poisson anymore,
Yes.
right? So the previous basically assuming is a inhomogeneous Poisson by using this. But the inhomogeneous Poisson still allows the try variable.
So is there a contingency result about the contribution of the seeker and gamma?
Yeah. When you fit the model, you have confidence bound on those. You can also have a p-value of those. Yeah. So yeah, that just basically is one way to show you how the model is a non-stationarity. So one way. You can think of this kind of model as a statistics of random effects model. So you have part of it is like fixed effect, the other part is random effect. And I mean, this is just the difference is that right now you have a likelihood rather than a likelihood function is a point process likelihood rather than the standard linear regression, the Gaussian likelihood. The next example is again to show you how to do the binary sort of behavior response. This is a typical in a lot of experiments across the animal study, rodent, monkey, or even human. So this example in the work presented is a collaboration between Suzuki and a Japanese scientist, professor in NYU, and Professor Amy Brown have collaboration in this project. So this, she recorded in her lab, she recorded a monkey doing the experiment from the, recorded the unit, single unit from monkey hippocampus, and is doing the association test. The monkey basically saccade certain, supposed to train the saccade one of the, when they present to a certain picture, they just count one of the target, depends on the image. So the chance level, the animal making a random guess will be a quarter, 1/4, right? The chance level. So then you record it basically just behavior response, which you show here. The blue around this is try number, and this is the red showing the error, the blue showing the correct. This is your behavior measurement. And one way to model that in statistics, you just model as a logistic regression. And this simple. A logistic regression is a static model. You're showing the gradually increase, basically the probability gradually increase. You're just showing a simple model would be like that, like a constant 2-parameter model. It's very simple. And this is a monotonic increase according to trial. So, and then it's very easy. It's easy to interpret this parameter, and just 2 parameters. And then you can fit that. It's a generalized linear model. You can fit it with the global solution, get the solution, and then you can get shade. This is chance level. You can get confidence bound based on the parameter. You can get confidence bound on that. Then you can define at that certain level the lower bound of the curve. It's above chance level, you can say the animal started to burn. It's a statistical criteria. However, you see that because this is a monotonic increase, and then also you can get this to the standard model assessment and compare the AIC and the p-value, things like that. And it's consistent, and even for this simple model, it's consistent with the behavior data. The question is that can you do better? And the answer, the short answer is yes. So what they do is that because when you fit, you can make a certain assumption about this, those parameters. You can assume this is followed by a random walk. And then just doing similar analysis. The likelihood is a generalized linear model likelihood. And the state equation about this 2 parameter is associated with a random walk. And then because there's this assuming some fluctuation, then you assume you can go beyond this monotonic assumption about the logistic regression about this learning curve here. And then you, based on that, you see this is non-monotonic curve because you see some, there's some blue dot in the top, which indicates the actually making correct response. And there's some non-monotonic relationship. Then you can, in a similar way, you can define the lower bound, confidence bound, define the statistical criterion against the chance level, which is the probability of correct 0.25. And then for this particular unit, the firing rate is shown in the red curve. And you can see this neuron firing rate, how this firing rate related to this learning curve, and how to relate to this learning curve and firing rate, and see some relationship about that. And see whether at what time, at what point the firing rate started to have a significant increase.
I have a question. So,
Yeah.
if we are seeing so the interesting in this experience is that when it's transition from the incorrect trial to the correct trial. So I think, but is there something sort of the comment about this sort of great transition by the statistical? I don't know. Because in this case, the incorrect state from the correct state.
Yeah.
There's some very sort of state right.
Yeah. So basically, after a certain trial, the animal suddenly learning. There's some jump. Basically, there's some change, like a phase transition. But this basically also we are making an assumption there's certain smoothness, sigmoid function here, like sort of sigmoid function, which is consistent to certain other type of psychophysics. I mean other type of independent analysis showing just smoothness, sigmoid sort of shape. So I'm not saying this is the only model you can use. Obviously, you can use other type of model to assume, but you can fit the likelihood. As far as you can run on the likelihood, and you can get the sort of right. But this is at least it's an intuitive way to model the response in the binary logistic regression. The difference is that you incorporate state space model for that. To incorporate this non-monotonic relationship. And then also sometimes you just have the time series of spy train. You just observe very long recording the spy train, and then you ask how to model that. Obviously, it's non-stationary. You know, assuming the rate is non-stationary, and how to model that the fine rate. Right? You might have either just a single trial. Sometimes you don't have a multiple trial, so you don't even have the average. Right? So how do you deal with those kind of estimates? You don't have a multiple trial. You just have one time series. So in this case, state-space model will come into help because you can base on assumption the underlying rate function is a smooth function. It's an underlying assumption. Then you can make assumption that the rate is modulated by underlying Gaussian process. In this case, it's a hidden process. First order of the random walk process. X is a hidden variable. And then this bin size, this model is independent bin size, depends on your bin size you care about. So then you can define the probability you observe in that the bin for particular unit J. Then you define whether this, if it's the resolution is very temporal, fine temporal resolution, you have a Poisson likelihood. You have a point process likelihood. If it's a very large temporal resolution, you have a Poisson likelihood. But this is Poisson because the rate itself is driven by the hidden process, Markov process. So it's a double stochastic process, essentially. Double stochastic Poisson. So the rest of them is very similar to like have an EM type algorithm, right? You have the underlying state, and then you have the parameter, which is associated with the theta here, associated with the theta associated with the underlying noise, how much variance you assume in this underlying rate function. You just using the EM type algorithm, or if you want, you can do it some Bayesian analysis here as well. The key assumption is using temporal smoothness for this. So you have one trial, spy train, how do you estimate the fine rate? You don't even have multiple, you cannot do average, right? So if you just bin it using spy count, and obviously will be very, the estimate will be very noisy. This analysis will compare in the paper, the Anna Smith's paper, they also compare the standard method like bars, which is based on the Markov chain from the color method, and estimate the fine rate. And they concluded it's like comparable or better. And this is for one-dimensional thing, right? But one-dimensional, there's no any, just a rate function in time. There's no anything related to the variable you compare against. So when you have high density, when this is just example of what they do, like time trial, and then you can compare that using different method and see the comparison. And the gray area is showing the confidence bound and derived from the EM type analysis. And then they can also define, based on that, you can do a lot of statistical statement saying that in any time point, because you have a constant interval, then you can say at any time point, any time point in this axis, you pick 2 points, what's the probability the fine rate greater than the other time point? Then you can have this construct a matrix like that and have this plot. And then how to contribute to that is basically all the statistics is basically computed from the EM type algorithm and the common the point process point process future. The state estimate that you run an EM type algorithms come from the EM algorithm. So when the tuning curve is more complicated, in some cases that's the EM may not be sufficient, then you can use in sort of Markov chain power method. So here, this example, what they show is that it's showing a V1. So the V1 receptor field, they have 2 parameters. One is the orientation, the other is the width. So the TW parameter there is a tuning width parameter. And ideally, for individual unit, you can want to characterize these two parameters, you have the basic formulation. And this word is not really specific. At least here, just want to have you idea that what can you do using MCNC, because I've been talking about EML in most of the example. In this, even they don't make an assumption about state space model. So actually, this word they don't make an assumption about state space model in terms of these two parameters. They just doing standard Markov chain monoclonal. I think the take-home message in their work, basically they compare their method and with the other standards of the maximum likelihood-based method, and they found that when the trial number is small, you see the mean square error in the approach is better compared to maximum likelihood. And this makes sense because the maximum likelihood method depends on a lot of, it's asymptotically optimal on the unbiased. When the number of tries is smaller, the estimate is poor. The Bayesian estimate, based on the MCMC, the solution typically is better when you have less number of the data. When you have a lot of number of data, the difference of these two estimates is smaller. This is based on the simulation analysis. So that's basically this sort of a take-home message, just this part. This is worse for not only for the single model, but also for the multiple model to include. So the next example, I want to tell you a little bit about this inverse problem. I don't know how many people have been working on the inverse problem. The inverse problem typically dealing with like a ill-posed problem. So you have a non-unique solution, many-to-one solution, and you want to impose certain constraint in the solution space in order to get a unique solution. Depends on your constraint. So for the EEG or MEG, basically you have your observation of the sensor space, your channel. You have the multi-electrode channel recording between your scale. Either have scale EEG or you have the multi-channel, the MEG recording. So you have, in this case, the MEG inverse problem is that you have the state variable is the variable of interest, your dipole. Right? The dipole typically, the realistic model, any realistic model of dipole is greater than order of thousands. Right? In this case, it's an order of 5,000. Because it's just like you can think it's like three-dimensional feeling inside the brain. So the goal of this inverse problem is that based on your sensor recording, the multi-channel EEG, how to identify the dipole activity inside the brain, and then you can visualize that when you look at watch a video. I'll show you later on. So there are a lot of approach in the literature. I won't be able to go over it. Standard approach is basically just doing some regression, a least squared solution, but put in some regularization like L2 node, L1 node, some sort of constrain the solution space. You basically just global solution, one shot. But it's fast. That's the standard approach.
Sorry, I have a basic question. So this MEG use mic. I have a basic question. This MEG data is three-dimensional data.
No, it's just one channel, just a multiple channel. It's a multiple time series. But the dipole itself is just depends on the dimensionality of the dipole is order of 5,000.
So MEG is in the surface data.
Yeah, but you treat it just like independent measurement.
So this is interpolation in this figure.
Well, this basically just visualization showing the dipole typically inside the dipole, what's the relationship of the dipole into the neighborhood connection. And this is some sort of intuition whether those dipoles should be connected to each other. The dipole in this case, you represent the unknown state, x. So it's your dipole. So the x is the huge dimensionality, large dimensionality is much larger than y. Y is your observation. So if you don't make any constraint, basically you can assume any a random walk or a linear AR type model, but this transition matrix, if you don't put in constraint, it will be very hard to learn with no structure. And unfortunately, there's some structure. So you made assumption that any dipole is only related to local dynamics, only related to a global local neighborhood. So you can define this neighborhood depends on how do you define this M around the neighborhood. So it's showing local interruption. So then the transition matrix will be very sparse, right? So you're showing certain sort of linear type regression, and depends on the individual position, which is associated with some AR type relationship, and then also depends on the neighborhood, and interact with the local neighborhood and plus some sort of noise. Then eventually you can write down this standard state space model in the state equation, but this matrix F will be very sparse because it's the order of, otherwise it's a 5,000 times 5,000 matrix.
But so A and D is a parameter.
Yes.
But so it seems to be a nonlinear model through A times D.
Yeah, so D is basically is a variable you can define. A is a variable between 0 and 1. And D, you can impose some sort of distance, sort of, using the prime information. In that case, it's showing D is inverse proportion of the distance between the dipole. Yeah, you can impose that. And then, because essentially you have some, this will become a product, you have ambiguity, you can fix one thing and then just, can make some assumption of one thing, the scaling, and then just update the other. Because it's proportional. And the G, which is the measurement equation, in this case, represents the Lie field gain matrix, which is the solution to the forward problem. And this is a backward, like an inverse problem. This is a forward problem. And I'm not an expert in this field, so I just repeat what they say. Just basically, this G can be estimated separately from the geometric like physical information. I'm not able to comment much more than that. So the only thing I know for this problem is the W, so the noise. And it turns out the noise is very important. So a simple, at least, we can show in just one parameter, it's just it's a scalar, but you can show it's a diagonal matrix. You have a diagonal variant theta, and you can show it's a full matrix. So choosing the trade-off between the different degree freedom in their word, they're choosing a diagonal matrix theta. And then they're using some sort of conjugate pi here. So because it's Gaussian, so the variance you can use in the inverse gamma. Or if you model the inverse of the variance, you can use gamma. So either way. Then you have a hyperparameter alpha and beta here. So the technical detail I won't be able to show you, but generally it's like an EM algorithm. Is that runs calmer, smoother once you have the state equation, and then instead you just update the theta. And then fortunately for this problem, you have a numerical solution, just what we expected for the conjugate pi. So I can show you some video, what they do in their paper, is a neural image. I won't be able to tell you more in terms of exactly what they did in terms of the biophysics, in terms of the full screen. So it's a simulation study in order to compare different methods. They have MME basically just know anything, it's like a least square type of algorithm. And this is FMAP, this is just, it's very fast. So MME is the very, you can start for a moment. So MME is basically is know any state space model, and this is using a common FS, I think is FIS, I think is using a common title. I forgot exactly what the notation. FIS is like basically just run a common smoothly without doing EM. They're doing some simplification about the M step. So, and then this two basically this is the one they showing. I think S is this solution. The solution is similar. S is just making an assumption about different noise. So noise whether it's scalar or diagonal or something like that. And you would be basically you're trying to looking at this solution is the optimal solution you claim. And you can look at, I have another example, just look at in time this simulation, how in temporary, how similarity between these two. At this, you can see that these two are also similar. Generally, if you don't have constraint and the solution is all spread out, then you don't have constraint. This is another example, another type of simulation. I think this is real data, so there's no one truth. But in their paper, they do have some physiology, so the inside they can compare which area of the brain should be activated, and then you can make some interpretation about the result. And generally, the solution is more local and just rather than spread out. And this is the one snapshot. You see the solution is much more local rather than spread out. And these two solutions are similar, just slightly different. The next, about another 20 minutes, so I should try to finish. So the next problem is the deconvolution problem in fMRI time series. So in this case, generally fMRI experiment you would have different kind of you involve because your observation is the fMRI time series. So you're dealing with the hemodynamics or neurodynamics, right? So neurodynamic influence your the time series, but also your hemodynamics. So you want to characterize this two part into your equation. So this basically is the extension of the standard linear, sort of linear Gaussian model by introducing a bilinear model. So bilinear model has some bilinearity here. So the S represents your sort of neural activity. So U is the modulating input, is the observed variable. So stimuli driving input is the V is also observed. And this phi, this matrix, is like a big matrix, is pre-designed. Each row corresponds to the basis of hemodynamic response function is pre-designed. And the unknown parameter here is basically A, B, and D, and beta. And X, you can construct this based on using the embedding technique, and you can associate with this time series, associate with the X. Bottom line is that you can write down the state-space model. And they're using different notation in that literature. They call this causal dynamic causal model, DCN, model of neurodynamic, but essentially just state-space model. And the hemodynamic cell is sort of like a generalized linear model. So this is just an example to show you what I mean by that, showing that what you observe is fMRI time series given the S is the neural response, neurodynamics, and this is the U and V is the modulated input of driven input. And then you can get, the question is that from this, can you recover this? And when you observe this too, is the deconvolution problem. So in their work, basically this can be solved by EM, even you involve some bilinearity. Right? By bilinearity, basically you can see here, there's some interaction, bilinear rather than linear. And then they also make some interpretation. This bilinearity can be explained by volatility series. So you can depends on you have a general nonlinear function, depends on your S and U, and you can do voluntarily series expansion, taking certain term, can throw away most of the second order term. It's just the bilinear term. The interaction between these two terms, and just keep that term, then you can interpret the voluntarily series expansion. And then you can run an EM title algorithm. E step is common smoothing, using again and again. M step just estimate this unknown parameter. And just showing the solution here. There's a common filter without smoothing, common smoothing. The smoothing basically runs better than just without the smoothing. And the winner filter is the standard approach. And the solution basically is smoother. And this is simulation, so you have to ground truth the data and compare. This is a real data. What they show is that the word fMRI example, basically the subject listened to some words, presentation of the word through the headphone. And then they have this, they also have this modulated input U, showing that those words are represented with a different sort of a rate. This is represented by step function here. This is the one is the this is modulated input. This is driving stimulus input. And then they apply this technique, and they found that this they convolve the scene. And I mean, I believe I forgot exactly the detail. They do some the result interpretation in terms of the method, using their method compared to the other method. How do they make sense of the result? But I just want to show you they do apply to the real data. So the last example in the last 10 minutes also, I just show you the last example is a very recent work by a former postdoc at lab, former graduate student in the lab for PhD work. This is the sort of brain-machine interface example of how to do brain-machine interface, sort of regulatory in real time or neuroprosthetic. They have a technical paper published in IEEE, and they have a more experimental paper in Nature Neuroscience 2012. But this is more technically, I focus on the method. Essentially, basically, you have the system is like that. So the motivation is that you want to have some sort of using the feedback, how to use visual feedback, and then how to control this, design a control signal to make sure this have an optimal control. The sensor feedback here is you see this approach. You want to design a controller you apply the system and then and reach the goal. And for the space model here, X basically just is your for example is your position, velocity, your acceleration is the kinematic in the two-dimensional field. I show you can show you I don't have a slide of the paradigm here. Basically, it's your X basically represents the position, the hand position, the velocity, and acceleration, kinematic. And then you assume in this position because you want to apply control signal applied to this state equation that will influence your state, right? Influence your the kinematic. And then because it's a control, if you apply this a standard if it's standard linear Gaussian space model, you're using the linear quadratic control, then you minimize the quadratic function, and this is the control part, and you basically minimize this function. You have this analytical form, write down the recursive equation, and you have this u is the t is the time, arrival time. Then you have this analytical form, u. And then the optimal control feedback, basically you want to apply this u, and this is your sort of feedback control state space model. So basically you want to use this control because you want to minimize certain criteria with this cost function. And then this control will apply to your, using this feedback to your system, and then you'll change the system, basically change the dynamic of the system. And writing more exactly for like a specific reaching movement task. So you have your desired target. So your cost function will be the desired target. With your desired target, you know what you want to control. You know that, and then so your at the end of the arrival time, you know what's the variable. That's the variable you have. You want to minimize this difference between these two. Then you also want to minimize. You want to minimize control energy. You want to quadratic sort of cost function. You also hopefully impose this sort of because you're using less energy, travel less distance, and using less velocity to reach the point. So you want to minimize the energy of that velocity and acceleration as well. So x corresponds to in the two-dimensional case corresponds to this location, velocity, and acceleration in the two-dimensional plane. So for that, we can write down a state equation using sort of biomechanics knowledge. You can write down, construct the equation using certain time constant, depends on the specific system. This can be, have the prior information to write it down. And then you can, because you have the desired solution position, the trick of the approach is that write down the desired position into your state equation. Write down D is the observed position, desired position you want to, at the end of the controller you want to, that spot, really coincide with your desired location. So write down this D star into your state equation, and then for this augmented state, we represent the act of, you can write down a new form of the state equation. And then the observation is just a spike. It's a multiple neurons from a primary motor cortex. You have the autosomal, and you have a point process like. So then, if you know the arrival time t, and you know the order of neuron activity from 1 to t, you want to write down this x, and just like the base rule, recursive base rule. Then the difference between the standard, without control by process filter and this feedback control is that the equation, the first two prediction, basically you have the variable. Once you know the t, then you can apply this feedback to your system and change the system. And then basically you know you have the feedback and you know your design objective and you want to control the x and to your desirable way and change the equation. That the second tool is basically is the same. Just change the first two predictions there. And then another contribution of the work is that essentially the t arrival time from the control system point of view, from the external point of view, is unknown. This is compared to the brain. The brain will have certain design. As an internal observer, you know what the arrival time should be. But as a control perspective, external point of view, external observer doesn't have knowledge of the t. So what would be the t to do is unknown variable. So one way, you have some different way to solve this problem. But one way that Marian do that is to discretize this time to multiple finite discrete possibility and then say apply to that. And in this case, you can set this apply, and then for the posterior, without conditional marginalized t's, then you have a certain mixture, some conditional t, and just have a posterior, given the n was the t, was the arrival time. And you discretize it, and assuming apply for that, and you model this posterior with apply and doing a two-way base loop. And fortunately, this part can be derived analytically, and then the technical detail I won't be able to show you how they derive it. But everything is analytical at this point. So you can make some prior, and this either is exponential decrease or uniform distributed, doesn't depend. And the rest of them can be computed analytically using this filter, using using this point process filter. Yeah.
In this model, you are sure that in each trial, the TJ is a difference.
The TJ basically is non-overlapping. Assuming the arrival time could be a finite, right? Assuming the arrival time could be any time from, you have an orange saying from 200 milliseconds to 100 milliseconds. What's the arrival time you should reach to the target, reach movement? You have certain constraint, right? It's not zero, obviously. You have certain constraint. But you can discretize it. Depends on your temporal solution. Depends on your solution. You just specify what would be the desirable reaching movement to be. This depends on your neurons, right? So, and then if you draw a diagram, basically just like a parallel sort of a point process filter. For individual one, you have different arrival time. And you come up with a, given that, you can come up with a posterior estimate. Then you combine them in this, in a base way, in a principal way. Then you come up with a final posterior. And they do in this work, they do some simulation. I won't be able to show you. This is very, going into the details, very complex. I won't be able to tell you the full story. Basically, it just the bottom line is that the solution is very appealing. So, and for the time constraint, I won't be able to show you a lot of other type of example, but I just want to give you sort of highlight this is what I believe, so this is the other field which could be interesting for the audience here. So, for people who care about in the front end, the neurotype analysis, the spice sorting is very important actually. And then you're doing the typically non-stationarity about the spice sorting, the waveforming change around time, and people can use the state space model in that stage as well. Like using either type of Hidamard model or Gaussian picture with the time varying Gaussian picture. Hideaki in the past also did sort of analyzing high order synchrony. So we see some presentation of his work using state space model. Shigeru, professor of model, also did some work on this and how to use the state space model to do some prediction despite timing in his early work. And so far, I think we emphasize a data-driven model in the states equation, but we can also use in a biophysical model. We can write down a biophysical model, and which is associated with certain parameters of the interest data. Then you can estimate the biophysical model as well if you want. Right? Just, I mean, there's some recent work done by people in Boston University to show this. We did a quite process to estimate this biophysical model. Other analysis you can do some things of the sort of causality analysis in terms of granular causality using multi-time series, either fMRI or EEG to do this granular causality analysis that a lot of work in this area is based on the state space model. And another important question is that also doing experimental design is also important doing the real-time sort of online experimental design. How do you update the optimize your experimental stimulus depends on your response. Depends on the animal response. When you update the stimulus, sort of what's the optimal stimulus. If you have certain parameter of the stimulus, and you characterize the parameter, update that in real time. Just ongoing sort of real time experiment. So I want to point out some of the challenges in the field that which I briefly mentioned yesterday, that has been discussed a lot of technique that either some of them is very standard, but I have to point out that you have to really tune to the specific problem to get the solution. Because as you see, even using EM, if you without imposing any constraint, the solution can be very poor. So I think the challenge for this neuroscience analysis is really how to explore this data structure in terms of either sparsity, smoothness, or complexity. You can get different important domain as a applier to the solution. Then hopefully you can come up with some scalable, fast, and efficient solution. And obviously, for neuroscience, the ultimate goal is to apply to the translational neuroscience so that you can, using the technique, to benefit the society. The prosthetic or deep brain stimulation, those sort of analysis, or seizure prediction, and those are very challenging, obviously, it's not easy. But just give you a sense that what people has been, this will be the ultimate goal in this field. The last point I want to just say that depends on the specific objective here, and sometimes what we describe is a standard approach, how do people do in the literature, but if you want to think outside the box, probably you can think a little differently or come up with a different solution because your goal, ultimate goal could be different. I can give you just one example in the hippocampus example. You want to just recover the animal's the position, probably you don't need to do spice loading. Or can you, right? Probably you don't have to do spice loading. Okay, you have a different assumption. You just want to calculate the raw spike, sort of the original raw signal in your position. You want to establish some relationship there. So probably you don't have to do spice loading. So then you probably, either you come up with some approximation or you come up with some different solution I won't be able to show you here, but just want to show there's different route you can take to reach the same solution. And then you probably have, depends on different route, then you have pros and cons, but really depends on what you care about. Thank you, stop here.
Any question or comments? Okay.
Just brief question about the receptive change. So does they do any follow-up work? So like memory first did and you read and send it up, and they only consider linear track.
To my knowledge, I don't know anybody who follow up. Yeah, I don't know.
Nobody does it to the
Yeah, I don't know, but to the two-dimensional is straightforward.
Yeah.
But just like other area, the receptive field, I don't know. I guess we don't have the, I don't know anybody.
Even Eric edit.
No, I don't think so.
Any other question?
Okay, thank you.
Thank you.
Then this is the true end of the this.
So I'm going to finally, I just want to
I will need a PDF file to